UC Irvine, who is not going to be talking about conformal field theory or the AES-CFT correspondence. I apologize. Just go ahead.
All right. Yes. So as Marcus said, there will be no bootstraps involved in this talk. So we'll be taking a detour from formal stuff into more phenomenological things. So we'll be talking about dark matter. So the title of my talk is On-Shell Mediators. We'll talk about what that means. And this is work in progress and recently published with friends from UC Irvine. So by way of outlining, so mediators are things which connect the dark sector to the standard model sector. More generally, when you talk about mediators, you talk about these simplified models. We'll talk about what that means. And these simplified models are also a type of interface, right? They're an interface between experiments, here, which is what we can do on Earth as human beings, and the actual true theory of nature at high scales, right, which is represented by I don't know if this is Wiccan or something. And the general story of this talk. You're right, actually. So who would this be? Michael Peskin, right? A young Peskin. So the idea is that here we are as poor particle physicists trying to figure out what the UV model of nature is. And in order to connect from our experiments to actual Lagrangians, we have to go through this interface. And what Adam is thinking about here is a different region in interface space that I want to highlight in this talk. So let's just jump in. If you ask dark matter, if you type in dark matter into Google, the first reputable thing you'll probably find is the snowmass proceedings from last year, and you'll see lots of diagrams like this, right? And this is somehow the summary of how we're supposed to think about dark matter circa 2013, 2014. And the idea is that dark matter interacts somehow with the standard model. Let's suppose that's a reasonable assumption. And interacts with some blob, some maybe higher dimensional operators, maybe there's something which you integrate out, and you can characterize the different types of experimental searches for dark matter based on which way you read these blobs. Right? So either dark matter is annihilating, or it's recoiling off the standard model, or standard model is annihilating, and you can just say, okay, well this looks like something where I have annihilating dark matter in the center of the galaxy. This is something where I'm recoiling off of some detector nucleus underground, and this is something which Yushin spent a large part of his PhD doing. And that's all very nice. Except when it breaks down. So when Yushin was at Cornell and Fermilab, one of the big things that he did was he said, well look, what you're doing here is really, you're saying there's one operator. Dark matter and standard model talk to each other through one operator. So each of these blobs, even though they map onto different types of experiments, they have one coefficient. So if I'm constraining this coefficient, I can probably plot them on the same plane. So I can plot, say, for example, collider bounds on the direct detection plane. And I can say the LHC has some bound on direct detection of dark matter. And that's really nice because you see some what look like very strong bounds at low energies that direct detection experiments have no hope of probing. And then there's a bit of a backlash where people said, actually, that's not quite true. At some point, you're putting bounds on effective operators that maybe don't make sense. And certainly, and these are things which Yushin and people in Irvine knew for a long time, if you have a mediator, you can have effects where there are resonances, or you can have effects where you hide better from the LHC. And the punchline is that mediators are important, especially for these collider bounds. So anyway, this can be your problem and not mine. So moving on, the punchline is this. Maybe we shouldn't be thinking about these blob diagrams and rotating them around. Maybe we can be a little bit more sophisticated and talk about these mediators. Right? This is the exact same thing as the simplified models for the LHC from 5 years ago. So for a simplified model, you specify what your dark matter is, spin, etc., etc. You specify a mediator, what the spin is, and couplings to both the standard model and the dark sector. All right, so that is simplified models as a framework for connecting experiments to dark matter theories. Good. So as a case study, I'll be talking about this popular anomaly, if you want to call it that, the FERMI gamma ray excess. Right? So I'll explain what this is and why people are excited. But what's really important, so let's be completely honest right up front, is that this may not be dark matter. Right? And this is the thing that you lose with all the hype machine. There are many reasons to be skeptical about the signal. And I'll highlight those. But that being said, I'm going to run with it. And the interesting things that pop out of taking this signal seriously for a bit actually lead to interesting directions in dark matter theory space, which are no longer dependent on this particular signal being real. You can say interesting things about models of dark matter annihilation, which are kind of interesting. So this is my big caveat, right? So I'll be promoting the gamma ray excess, but this need not be an actual signal. So here is my icon for the gamma ray excess and why this points to this on-shell mediator scenario. Okay, so I had a very nice walk from downtown Davis to here this morning. And Davis is an educated college town. And if I told people that I was giving a talk on dark matter and signals of light coming from dark matter, the first thing they'd say is that's crazy because everybody at Davis knows, being an educated college town, that dark matter is dark because it doesn't interact with light. But that's okay. How do we actually get light from dark matter? The process is actually very similar, right? If I covered up these chi's, you would know exactly what this is. This is something you would put into Pythia, right? So if dark matter annihilates into a pair of quarks, we know that the quarks are injected with some energy. In fact, the energy is set by the kinematics for a 2-to-2 case. These things have color lines. They shower, right? They shower, they hadronize, and the color lines become color singlets. The hadrons decay into lighter hadrons, like protons and deltas and whatever. Those things like pions then decay into pairs of photons. The pions are the lightest hadrons, and you get tons of them, and you get a spectrum of photons. You also get things like protons and antiprotons and charged guys, charged leptons. Those guys are hard. Photons are really easy, because photons annihilate in the galactic center, and they come straight to us. Right? So if I didn't put chi's here, if I put protons here, you will immediately look at this and say Pythia. And I can run Pythia or Herwig or whatever your favorite program is a zillion times, and you can tell what these spectrum of photons are, right? And this is something Rachel and I did along for a year or so. Taking final states from this hadronic junk and plotting what the spectrum is. And here is the photon spectrum for 40 GeV dark matter annihilating into different final states. And this is really just hacking this into Pythia. So to the extent which you really trust all of these QCD string models, blah, 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 you can, in principle, distinguish between the spectrum of B quarks at a certain energy versus tau leptons or W's or whatever. So, and if you're buying this so far, I have a used car to sell you. But at least this is the idea that we can actually tell a lot about the spectrum of dark matter annihilation just looking at photons. Okay, so now that we have something optimistic, where do we look for this dark matter? Right? So we know that we live in a halo of dark matter, and it's densest in the center of the galaxy. So center of the galaxy, about 8 kiloparsecs away, so kiloparsecs around 3 light years, I think. That's where we have the biggest density of dark matter. So maybe we should look over there. And our eye in the sky is the FERMI satellite, in particular the Large Area Telescope, which is our photon detector in the sky. And the way this thing works is we have our telescope, so this is now centered around Earth, and we have a viewing region. So for the Galactic Center, it's 15 by 15 in galactic coordinates, which is slightly different from polar coordinates. And you look at the galactic plane, and we just count photons. And the point is that we have a dark matter halo. So in addition to this spectrum, where in energy space we can learn something about annihilations of dark matter into photons, we also have a distribution in actual space, a morphological distribution in space as we look at the telescope. So this gives us a handle for background subtraction, which is good because also in this gigantic halo is lots of matter. Right? So we have lots of really interesting astrophysical objects on this galactic plane. And interesting astrophysical objects are a euphemism for really boring particle physics background. And we have to get rid of that. And the fact that we have a different morphology for the dark matter is a handle for us. Good. Okay, so we've talked about the tool that we have for looking for dark matter annihilation. We've talked about the general idea. What is there to see? So here is the status of the Galactic Center Excess. I think this is the name that people have started using. Circa last year. And here's what happened. You have independent groups. So there are 3 or 4 independent groups. Here's one from MIT and friends, and this is from Irvine and friends. And they all have these fantastic spectra. I mean, as particle physicists, we look at this and say, oh, look at those error bars. Look at that fit, that's amazing. And what they could say was, well, precisely because of this story, because I really, really, really know what a pair of B quarks looks like, I can distinguish a pair of B quarks versus a pair of gluons or light quarks, I can really, really say that this excess really looks like it's fit well by dark matter, 40 GeV dark matter, annihilating into pairs of B quarks. And then, so these people publish a paper, then their friends over at UCI publish a paper, and they also say, oh my gosh, 35 GeV dark matter going to B quarks. Oh my gosh, look at that coincidence. Isn't that amazing? And then, looking from the outside, you think, that's great. Multiple independent sources have confirmed this signal. Now, they all have to do their own background subtraction. And as of early 2014, the only background you could use was the background that's provided by FERMI, which is great. Open science is fantastic. They have all of their tools available online. All of their data is online. And they have a background you can just use to subtract. And last year, this background is called PAS7. PAS7 is a point source background. So this is a diffuse emission, right? You look at the Galactic Center. This is a background that's phenomenologically fit to look for point sources. Right? So this is not the correct background to use for looking for diffuse sources. It was the best thing one can do. It was all they had. But everyone ended up using this very same background subtraction. And sure, there are different things you can do to add on. The UCI group subtracted off additional molecular clouds, and they still found a good fit. But it's no surprise that these groups agree, because they're comparing the exact same apples that they've bitten into. So here's a glimpse of what the current status is. So these are slides from Simona Murgia from the FERMI Symposium. The paper, I'm told, is nearly finished, but this is, so sorry it's a bit faint, but we'll have better plots later on. This is a rough estimate for the systematic errors in this analysis. So here is fitting to a exponentially cut off power law. Here is fitting to a multiple power laws that are splined together. None of this is important, except to say there is a large wiggle room in what the spectra can be. And what these people didn't really have the opportunity to do was to put on systematic errors. Right? These error bars are all statistical. And of course, as particle physicists, especially as theorists, when we look at a paper and we see error bars, those are all of the errors. In astrophysics, it's more common to put statistical errors because the systematic errors include known unknowns and unknown unknowns in Rumsfeldian terminology.
So, next slide again.
Yes.
Why do we not just simply take the data directly? Why do we have to assume pulsars or OB
Oh, yeah, so
stars?
yes, good. These are assumptions for the morphology. So there are assumptions both for the morphology and the backgrounds that you're subtracting.
I think these are different background models, right?
Yeah.
So the spread between those curves is some measure of the uncertainty in the background.
Yeah, but doesn't the data tell you?
Oh, good. So
it is?
yeah, good. So you have some spectrum of photons, and I have X, Y, and Z, some list of background sources, which each contribute to the photon. So think of it like a stacked histogram.
Yeah.
But I don't know the overall normalization of these background sources, so I have to let everything float and do a chi-squared. So it's a little, in this sense, it's a little bit different from the LHC, where in the LHC I can run my Monte Carlo, and to the extent which I trust the Monte Carlo, I roughly know how when I stack these histograms, how much comes from this background, how much comes from this background, how much comes from this background. Here, they actually have well, let me be flippant and say they have no idea, and they have to let that normalization float.
So I guess another way of phrasing this question, which maybe you'll answer, is there a background model that just simply fits the whole spectrum without
good.
any dark matter?
Good, yes, and the punchline is the answer so far is no. And this is from the FERMI collaboration saying there is still an excess. And hopefully in the next month or so, we should have a more definitive statement.
Sorry, you say this plot is this plot.
These are residuals. Yeah.
Oh, okay. And then when you say systematic uncertainty, you just say like
Yeah.
gives you a big.
Yeah. So let me show this plot. So shortly before that slide was made available last December, Calore, Veninger et al. did their own estimate for systematic errors. So they took the Fermi data and they put in their own background models, and they put in some estimate for what systematic errors should look like. And they got these gray bars. So this is 2015, and so this is now being a little bit more sophisticated. And in fact, you can see they're more sophisticated because none of their lines seem to fit very well. And this is an effect of the covariance matrix, right? All of these bins are correlating. So this is a more accurate representation of what we know about the excess.
But do you know the normalization of those colored curves?
Good. These are all normalized to the thermal cross-section. So we'll talk about that in a minute. Yes, these are normalized to what you expect for dark matter annihilation to get the correct relative abundance. But the other thing is that it's not like you can take this yellow curve and just increase the normalization by, say, a factor of 2 to get a better fit. Because that, even though we're just plotting residuals here, doing that screws up the background fits.
Sorry.
Yeah, so naively I would look at this and say, okay, take this yellow line.
Right, that's what I.
And that normalization should be, put a factor 2 in the normalization, shouldn't that be a better fit?
Yeah.
And the answer is not quite, because all of these error bars, these are just the diagonal elements of the covariance matrix.
Mm-hmm.
The fact that each of these bins are correlating means, say, the backgrounds that are being fit to this are continuous spectra. When you actually let everything float, apparently these are the best fit. So it's a more subtle story.
So I shouldn't even say that the peak of the BB is more similar to the peak you get for the data. Or the location of the peak change if I try to just do an overall rescaling?
Oh, good. I think that was taken into account, right? So the mass of the dark matter, which roughly tells you the horizontal position of the peak,
yes,
is something which they let float.
Right. So from this, can I say the BB bar at least it gives you the right location of the peak?
Look, the thing which you can say is that the BB bar chi-squared is a little bit lower.
It
But
sounds like he's saying they're letting the mass flow
Yeah.
independently for each model,
Yeah.
which makes sense, right? Why should you? So in other words, the best fit value of the mass might be different. And it's a harder spectrum, you would probably use a lower value of the mass.
Right.
Get it?
so
So the correlations that you speak of
Yeah.
are
in the backgrounds, for example.
but I mean in different regions of the polar coordinate space, or what
Oh, good.
correlations?
Everything folded in together. So the morphology also, but even for the spectrum, the fact that, let me make something up. If I have some background near in the Galactic Center which looks like this, and I play with this normalization, I still have to do a best fit. Right? I have to let everything float. So I have to let the normalization of my new weird background also float. And apparently this is, so when you do the chi-squared, you close your eyes, do the chi-squared, these are the best fits.
So what's going to the chi-squared?
What's going to the chi-squared?
Yeah. Going to the
Oh yeah, some set of backgrounds. So this is things like the molecular gas in the center of the galaxy, point sources, things that pulsars that you know about, pulsars that you don't know about but assume some spectrum.
How many degrees of freedom to this chi-squared?
That's good. That I don't know off the top of my head.
Some of the others had it going to towers, but I don't see that here. Is there a reason why?
So these are not my plots, but let me go off of their script, and say that I think there's a lot of wiggle room to put in whatever spectrum. And taus are actually a reasonably good fit, because taus, they go into hadrons, and so they look like a hadron spectrum, and they have a more diffuse spectrum. We'll talk about this towards the end, actually. Leptons tend to be hard because they have a very sawtooth spectrum. Okay.
So the reason the curves can be low then is because the normalization is just one parameter. Those are all systematically correlated.
Yes. Good.
And there's about 30 bins, therefore about 30 degrees of freedom. That's 30. So they're all about one signal length.
Good. So, and I think the unofficial statement from people in FERMI is that even this is an underestimate for systematic errors. Okay, so very quickly, let me just run through possible alternative explanations. Right, this is Kage and Emptor. One possible source are millisecond pulsars. So millisecond pulsars are these astrophysical objects which are spinning around very quickly. And in fact, you can guess how many millisecond pulsars should be in the center of the galaxy based on what's not in the center of the galaxy. And you say, it seems like you need like several orders of magnitude, like 3 orders of magnitude more pulsars than you expect. And that's true. And in fact, when pulsars are formed, they tend to be kicked out of the galactic center. They're formed with non-trivial angular momentum, and they tend to want to leave the galactic center anyway. So you have a reason to expect it not to be pulsars. But the pulsars which stay in the galactic center come from this kind of binary system where you have two stars, and one speeds up into the millisecond range by eating its sister. Right? It's kind of grim. But this gives you some kind of story for where these pulsars come from. And this is really at the level of a fairy tale. But if you believe this story for where these pulsars come from, then you can track the early stages. So before they become millisecond pulsars, they're X-ray binary systems. And the X-rays we can track in the galactic center. And it turns out that the morphology of these X-ray binaries are bang on degenerate with the simplest dark matter models. Meaning this is really an irreducible background. So take that for what you will, but this is caveat emptor. Alternately, so I'm just going to flash this on, there could be other sources of protons and electrons. So,
Well, just to return, but you sort of know how many millisecond pulsars to expect based upon the X-rays that you see. Is that right?
well, this is a question. It's not clear to me how well people know that, given this population of X-ray binaries, how many millisecond pulsars should there be right now?
Right, that's my question. Yeah.
I don't think they know. So the statement, as I have heard it, and this is from Abuzajian et al., is that the morphology is the same, and this should give you reason to pause.
I thought there is some like a standard story, like there's a correlation between the number of these objects, and then you don't see enough of the low mass.
Most people say there aren't enough, but that's a story. That's a question of how many of these X-ray binaries have already become millisecond pulsars today.
Mm-hmm.
And so maybe, probably you're right. I don't know.
You say the morphology is degenerate, are you talking about just the center or the halo itself?
Just the center, so just the area where we're looking at. Okay, and just very quickly, there are alternate sources. Here is you might have other sources of protons. So these are things which people just southwest of here are thinking about. And another interesting thing is you could have alternate sources of electrons. And this kind of goes to your question, because I thought electrons don't give you a good spectral fit. So here is a story where there's a big cataclysmic event in the center of the galaxy, 100 million years ago? Million years ago. And these injected a bunch of electrons, and these electrons can upscatter starlight in the ambient galactic center. And this starlight spectrum is now roughly fitting the Galactic Center Excess. And this is an interesting angle to play with, and we'll mention it briefly later on. Okay, now that I'm done being Debbie Downer, let's actually get to the actual Hooperon. So Hooperon is a word that people used, at least in Irvine, and probably behind closed doors, kind of sarcastically. This was recently on the BBC Horizon documentary about dark matter, where they highlighted Dan Hooper, and they used the phrase Hooperon several times. They even use it in the same sentence as the word Nobel Prize, which is a bit presumptuous. But I guess now Hooperon is a word. So what do we mean by this? Well, we mean the original best fits. So dark matter annihilating to a pair of B quarks, 40 GeV dark matter, so you have 40 GeV Bs, and this seems to give you a good spectral fit. And as I've shown you, there are hints that this is actually too restrictive, but let's go with that as our benchmark. What people found was that the cross-section for annihilation is order 1 times this number, 10 to the minus 26 centimeters cubed per second. This is a very important number because if this annihilation is S-wave, meaning there's no velocity dependence, this is really the exact same ballpark as you need for a thermal relic. Meaning this very same annihilation process gives you the correct abundance of dark matter today. So isn't that a really nice story? So, okay, so the simplest thing you can do is play, for lack of a better phrase, Yushin's game, and think about contact interactions. So I build a dark matter model where I assume there's some mediator which is heavy and decoupled, so all I care about is dark matter and the the B quarks. I write some kind of effective operator like this. And my point is that maybe this isn't the right way to go. You can write down a semi-exhaustive list of all of the operators which give you S-wave annihilation. S-wave, so you get this nice thermal coincidence. And then you can say, okay, maybe I don't care about spin 2 mediators because they're a bit cumbersome. So maybe I rule out the direct detection, things which are bounded by direct detection. So this is the spin-independent operator, which is very strongly ruled out by direct detection. I can rule out the axial vector from collider bounds, and this is even ancient, right? This is from 2012. And then I can say that actually these operators are related because these are two parts of a projection operator. But I know that my couplings have to be gauge invariant. So if I have a gamma mu gamma 5, this is really coming from some kind of Q bar, P left, P right Q. So generically, I'd expect these to have order 1 coupling. So if you're ruling out one, generically I expect you're ruling out the other. Right? This is not rigorous, but this is just saying maybe this is not the limit to think about. What am I ruling out now? These gluon operators are ruled out by the LHC, and on top of that, their spectrum doesn't quite fit. Right? Going to gluons is a very different shape than going to B quarks. So you're left with these guys, these scalar operators, and they look okay. So if you look at these bounds for these contact interactions, they look like they're living in an area which is far away from the LHC bounds. But they're actually also kind of in tension, because these things give you loop level interactions to this operator, and these guys end up being in tension. So again, this is not to say that this limit does not work, but just to motivate that maybe this is not the most interesting limit to think about.
Although the current collider constraint on that operator is not quite right, because it's a loop level process.
Yes, so this was the naive tree level bound. Yeah.
So D1 was the scalar?
Yeah, and we threw that out because it doesn't give you S-wave annihilation. So if it's P wave, your velocity suppressed, and this is like a 10 to the minus 6 factor in the cross section today, and there's no way to get that and relative abundance correct. Which, that's also a perfectly valid direction to go if you want to give some other way of getting the relative abundance of dark matter.
Right, they didn't know that was ruled out. Yeah.
Well, just under the assumption that this Fermi excess is real and the annihilation is the same process that gave rise to the relative abundance.
Mm-hmm.
Okay, so there are some exceptions, right? So we can, maybe some of these operators vanish because the dark matter is Majorana. Maybe you tune the chiral couplings, right? Maybe the gamma 5 and the non-gamma 5 standard model bilinears are tuned in some ways. And this happens for the leptons, right? For the Z couplings to the leptons are, I think, axial because sine squared theta W is almost 0.25. But more generically, one thing this could be telling us is we should be thinking about mediators which are light compared to the dark matter. And we can actually resolve what's happening in this little blob interaction. And then our framework looks more like this. We have a dark sector, some accessible particle, and that thing talks to a standard model.
Okay, so you haven't, in other words, ruled out a Higgs mediator at low mass.
Right, exactly. And that's where I'm going.
Okay, I was getting worried.
Yeah, no, don't worry. Don't worry. So this is the basic picture. And then you can give this to grad students or postdocs. I guess these were some combination of the two. And they can write down an exhaustive list with all the different spins and all of the different interactions. And they can tell you whether they get ruled out or not and where the bounds come from. So you're all taking notes and you'll remember all of this. I'll quiz you at the end. But then it looks like I'm done. It looks like 30 minutes into the talk, we're all done, and we've done everything there is to do about mediators.
So LHC is always maybe. That's
Yeah. I think this was Hooper's paper. Good. So, what else is not captured by this exhaustive list? Well, maybe you annihilate into the mediators. Maybe the mediators are so light that when dark matter annihilates, you can produce mediators, and that's it. Right? And this part right here sets your annihilation cross-section. The meteors are produced, they propagate. They keep propagating, whatever. They have a very small coupling to the standard model, and eventually they decay. But the annihilation cross-section is not set by that. It's only set by the dark matter coupling. Right? And what I'm getting at here is, in this scenario, you can make the dark matter coupling order 1, and the standard model coupling really tiny, and that's fine. The mediator will propagate for a long distance. But remember, we have these many parsecs to play with. The parsec is a long distance in particle physics scales. So now this gives us an interesting limit where we can hide from certain bounds. Right? Because now we have these two couplings. We have a dark matter coupling which sets the annihilation, and a standard model coupling which sets all of the other interactions. Right? All of these things are proportional to products of this and this. Annihilation only depends on the dark matter coupling. So very naively, I can fix this to work and avoid these guys. So isn't that a cute little interesting niche to go in? So let's figure out what kind of mediators we can go into. So if I go into pairs of scalar mediators, spin 0, these are all p wave, so let's forget those. If I go to pairs of spin 1, either vector or axial, these are both s wave. Good, we're in business. And because I'm going to pairs of mediators, which in turn go to pairs of B quarks, my dark matter mass better be a factor of 2 larger than I expect. I want to inject the same amount of energy into each B quark. Now, the new thing that we pointed out was that if you want to annihilate in spin 0 particles, the lowest topology is the 2 to 3, and only 2 to 3 pseudoscalars. And this guy is S wave, and now you have dark matter which is naively 3 times heavier than you expect for the typical Hooperon. And then of course you have to make sure that the masses are enough that you can produce these things on shell. But this is a really interesting topology that not many people have thought about before. And all we're saying, so we're taking a limit where this annihilation into on-shell mediators, which goes like the dark matter coupling, is much larger than the off-shell contributions, which go like the dark matter coupling times the standard model. So taking the standard model coupling very tiny is a natural way to get this. Good.
But are you ruling out the right-hand case?
Oh, no. Yeah, I'm saying
this is just an assumption.
I'm pushing myself into a particular region in theory space.
Right. Okay.
So back of the envelope, and this is actually all you have to know about these on-shell mediators. What is the mass of the dark matter? Well, if I go to n mediators, the mass is n times heavier, because I want the decay products to have the same energy as they would if you didn't have multiplicity, right? If I'm going to 2 mediators, I go to 4 Bs, so I better have heavier dark matter, so each of those 4 Bs has the same energy as the usual topology, as the 2 to 2. What about the annihilation cross-section? So if I go to n times as many final states, then my flux of photons is n times bigger, right? Twice as many for 2 to 2. But my dark matter number density, this thing which I called the J factor before, the number density of dark matter goes down by a factor of 2 because it's heavier. And in fact, in order to compensate for this 1 over 2 squared, I need to have factor of n. So the punchline is, sorry if that was a bit convoluted, the punchline is that my annihilation cross-section going to n mediators is n times larger than the annihilation cross-section that you need for going to 2 B quarks. Okay?
If you're really looking at the parametrics in n, isn't it somehow also just getting broader with n because there are so many ways of distributing the energy? Right?
Good.
It's not going to be monochromatic anymore.
Exactly.
Right.
Exactly. So as Marcus pointed out, now that if I go into 2 mediators, now these mediators are produced and they smear out the spectrum of B quarks. So here is the energy spectrum of the mediators. And this has to be convoluted, as you're suggesting, with the spectrum of B quarks giving photons. And then for going to 3 mediators, it's even more smeared out, because now, at least here, the kinematics constrain what the energies are. Here you have a range of energies. So yeah, so not only are you playing with the masses of the dark matter and hiding from direct detection, but now this is a very simple handle for changing the spectrum of dark matter, the energy spectrum. So remember, before we even talked about error bars, we said this very naive thing. If I run Pythia a zillion times, I know exactly what the spectrum of photons are. Well, here's a very simple way where I have a knob to turn, which is the mass of the dark matter relative to the mass of the mediator, which smears out the spectrum. So even that gets thrown out the window. And here is just an example of the spectral shape. And this is just to show kind of our very crude methodology, which is we took the rough residual plots from FERMI and turned that into an envelope. So we gave a factor of 2 above and a factor of 2 below to create this solid black line envelope. And we used this as a criteria for whether or not a spectrum is a good fit. So this is a very low-level thing. This is complementary to the more sophisticated covariance analysis. But this is something where it's very clear what you're doing and that you're really assessing the spectral shape. So, as a rough example, here's an example for 150 GeV dark matter going to a pair of vectors. And as I play with the mass of the mediator going from 15 to close to the mass of dark matter, you can see that the spectral shape has changed, both in the center of the maximum, the position of the maximum, and kind of the steepness of the slope. Now, you're not actually going to get a really huge difference because as long as you're going to quark final states, especially B quark final states, you're never going to get such huge boosts in your standard model states. But you can see that there's an effect. And let me just show a couple of plots just to show the punchline. So here are 2 ways of quantifying the fit. On the left is the minimum envelope scaling, meaning to say, how well does the dark matter spectrum fit if I made the envelope bigger or smaller? Like how tight can I make the envelope to get a good fit for the dark matter? So, order 1 is a good fit. Over here is what Jack was asking about. How far away are you in terms of the cross-section, the annihilation cross-section? So around 0 means that you admit normalizations, right? So the height of the spectrum, the height corresponds to the annihilation cross-section. You admit normalizations which are consistent with the thermal relic cross-section. So for vector mediators, we have a range of masses which give you the correct thermal cross-section.
So what's the color?
Yeah, so the color, so the key is here. As I progress this way along the rainbow, it means that you're further and further away in cross-section space, meaning you need a larger cross-section than the thermal cross-section. So around here, the cross-section to get the Galactic Center Excess is a factor of 2 larger than you need for the thermal cross-section. Good. So here's a very small summary plot just to give you a range of ideas, an idea for the range of parameters you can have. So this is this topology going universally into quarks. And this is just to say, so I put some envelope in gray, which you can kind of see in the background. For different dark matter masses, you can still fit the envelope. So going from 33 to 171 GeV, there are normalizations which fit the envelope. So this is testing the spectral shape. Then you ask, okay, that's nice, but which of these things are consistent with the cross-section? And here I have the key here. Your target is around 3, and you're within 1 to 3.5 for the green bands. And here you're within 10 to 24 for the red band. So this kind of tells you prefer the lighter dark matter. But the point here really is that you have a lot of wiggle room in the types of spectra and the types of final states for this Galactic Center Excess. So before getting on to more fun stuff, let me flash the analogous slides for 2 to 3. And so for all of these things, these lines are basically vertical, right? These contours of cross-section, mainly because you're not getting very much boost, right? If your B quark is 5 GeV and your dark matter is order 100 GeV, your mediator is somewhere in between, and you're really not putting that much boost into it. But for the 2 to 3, you have a problem getting the correct thermal cross-section, a cross-section consistent with the thermal cross-section.
So when you say thermal cross-section, are you actually solve the Boltzmann equation using this setup and then get the number for the
No, but I was even more concerned.
3 times 10 to the minus 26, right?
Yeah, this
but
number
how
here.
precise is this number if you consider a specific model?
The best number is 2.1. And so this is only logarithmically sensitive to the dark matter mass. right? This is from saying that, well, we can talk about it later. This is from saying that ballpark, you can say when the Hubble's rate is of the same order as the annihilation rate.
Right. Yeah, of course, but I mean, Boltzmann equation, you have some inverse process and then some.
Yeah, but then, I mean, but this is actually this is only logarithmically independent to those details. But in fact, I've been even more, I'll show you, I've been conservative here. So again, it's a range of normalizations, but the point is, the pseudoscalars have a hard time with the cross-section. And why is that? Okay, so the vectors fit because you have, again, this is all ballpark. Ballpark, you have these range of annihilation cross-sections for the Hooperon, the standard Hooperon, 2 to 2. When I go to this case, I multiply the cross-section by 2, and so I'm between 3 to 10. So this is a bit of a stretch, but 3 is roughly the target cross-section for a thermal relic. So going from 2 to 3, the cross-section is 3 times larger, so that's something which is putting you in tension. But in fact, it's a lot worse, right? So this is where I've been kind of lying to you. The cross-section now is polluted by P-wave processes, right? For annihilation today, I only cared about S-wave, but for the relic abundance, there's also an irreducible contribution from P-wave processes. So okay, P-wave is suppressed, but in the early universe, it's not so suppressed. In fact, so this XF is something like 20 at freeze out. So this is something like 20-ish over 3. Let's call that 9. So this is 3. Square root of 4 pi is about 3. So and lambda dark matter is order 1. This is an order 1 factor. So these two diagrams contribute, and this 4 pi is kind of hacking to compare phase space at the amplitude level. But these two diagrams are roughly of the same order. So, and it's the contribution to the cross-section, so the pseudoscalars really are kind of pushed out of the thermal relic story. You can do kind of hokey things. You can say that, oh, well, maybe part of the galactic center signal comes from millisecond pulsars, and part of it comes from dark matter, but that's really kind of pushing the story. But okay, that's the status. Let's do more interesting things and talk about experimental bounds and kind of model building from this. So these slides are just to flash. You have different types of operators for direct detection, but the point was always that these things just give you some bound for what the minimum coupling for the mediator is. Right? We've separated the coupling to the standard model from the coupling for annihilation. So all of these things, I'm just saying, okay, the standard model coupling is no bigger than this. Right? Here, you can do it more carefully. Let me skip this slide. And it's still just setting an upper bound on the coupling, which does not affect the annihilation rate. You can look at collider searches. So there a bunch of people did tailored mono B searches. And again, this is still setting even bounds which are not too strong for the coupling to the standard model. So kind of by design, this scenario avoids all of the traditional searches for dark matter, other than annihilation. But what can we get from this mantra of we have simplified models? Maybe we don't have to look for dark matter in detectors or dark matter hitting nuclei. Maybe we can look just for the mediator. Right? Instead of looking for this thing, just look for this coupling. And this is remarkably not bounded. So here is a search here's a plot from many, many, many years ago, looking for gauged baryon number. So say nothing about anomalies, but using LEP bounds, what is the bound for a gauged baryon number coupling? And this bound is basically telling me that my coupling is less than 1. It's basically telling me that my coupling to the standard model is perturbative. If I have a mediator which couples only 2 quarks. So one thing which I think is fun, and that I was hoping to catch Manny to talk about, is you could look for the mediator in diphoton. The scenario that I'm presenting here is really a leptophobic, gauge-phobic Higgs boson that's fairly light. And you can look for it through, the exact same diagram that we discovered the Higgs in. Now, what happens is, in the on-shell limit, this guy's kind of light. Let's call it 30, 40 GeV. These photons don't have enough PT to pass your photon PT cuts. So you really have to do this inclusively. You really have to do digest diphoton plus jet, diphoton plus 2 jets. So at some point I was bugging Ennio about this, and this is why. And these cuts give you an interesting feature in the Atlas spectrum. And the point is you can do a bump cut over in the shoulder. And it'll take a lot of luminosity to say anything, but when your benchmark is your coupling is smaller than 1, you can actually say something about this scenario. And of course, this scenario can be completely decoupled from dark matter altogether. You're just looking for a light, gauge-phobic, leptophobic, Higgs-like particle between, say, 10 to 40 GeV. Okay. I also told you guys that dark matter annihilation into quarks gives you antiprotons. These guys are kind of funny, they get bent around, but we have a nice machine for looking for...
So was there, on the last thing there, this search, this is, well, you say work in progress.
Yeah,
you don't know if it's going to work or not.
Yeah. It has to work. It's just doing it 100
some
inverse
of the
to bar or
possibility.
1,000 inverse to bar.
All right,
And it's tricky because this is an NLO process. It's not as simple as just running it into MadGraph. Like the backgrounds are like sensitive.
Okay.
Sorry, does that decay determined by the branching ratio, but not the coupling?
So, I mean, sorry.
Sorry, so the thing we try to constrain is the production of this lens.
Yeah, yeah.
So,
Well, I think, if you believe the Fermi story, you know the coupling, the production coupling from the relic density. Is that right?
Oh, no, so these couplings are completely independent. So in the
I know,
on-shell
but I'm
limit...
saying that you know don't you know the one on the left,
Oh, these are gluons.
yeah, no, but the one a little bit further to the left, that one.
Yeah.
You know from the relic density, and then the next one over you know from the Fermi density.
Ah,
No?
not quite, because in the limit of on-shell mediators, so yes, typically yes, and generically yes, but in the limit where you annihilate into, say, so here's dark matter, here's your vector mediator, this only depends on the dark matter couplings.
This is the scalar now.
Good, yeah. So I
Alright,
think-
so for the scalar, so then saying, so they're, sorry, that's the, so sorry, I think I have it, never mind.
Yeah,
I'll shut up. Yeah.
no problem.
Okay, got it.
Okay, so,
I mean, it's certainly true, however, that if you have an on-shell Higgs,
mhm.
Annihilating the BB bar or whatever in the universe,
Yeah.
then you can get the right omega, right?
Yes.
So this is, and so therefore it might be better to look for this light Higgs in BB bar or tau
Ah, good.
final states.
Good.
I mean, there are a
So
number of
if-
papers I've written on
Yeah.
this subject.
So yeah, good. I was taking the very naive stance that if this thing is, say, 30 GeV, the dijet bounds are really hard to sort out. And maybe that's a too naive statement. But, I mean, looking for dijet bumps...
What do you mean by hard to
Oh,
sort
meaning-
out?
too soft.
Yeah,
I'm
looking
sorry?
for dijets where the invariant mass is 30 GeV.
What is the mediator?
Yeah, the mass of this particle. The resonance will be 30 GeV.
Well, I don't know. CMS and Atlas are doing such analyses at the moment.
But they usually, well, yeah, we should talk about this after this. But,
Sorry, can I have another question
Yes.
before we leave this? I think I'm getting my footing back. So,
Good.
what about the monojet searches? Because those, I think, are pretty much constrained by the
Good.
astrophysics, right?
Good.
So do you know what, have you looked at the
Yeah.
monojet
Yeah.
constraints? on
So
this?
the monojet constraints, sorry, I flashed this very quickly. And this, you're right, so this is basically, how do I want to go? Proton, and there's missing energy here, and you have some jet.
Yeah.
And this missing energy means you're really producing a dark matter particle. So that depends on both the dark matter coupling and the standard model coupling. This thing is different because this only depends on the standard model coupling.
Yeah, that's right. So but the mono, does this thing sail through the monojet constraints?
Ah, I see. Good.
That's what I'm saying.
I see. Good. The response to that is, what if I took the limit where this thing is a top loop only? So it couples to, say, a right-handed top. I worry about gauge invariance through some UV physics. Then the monojets, I believe, are weaker. Monotop.
Sorry, so your coupling is proportional to the mass.
Suppose. But it need not be.
Because I mean, I thought you were trying to probe, because you're hoping to probe standard model couplings of order 1.
Yeah.
So then this production would be pretty big.
Yes.
And so then
Oh, good,
that's,
good.
and then, right, and then the point is that then you've got your dark matter coupling, but you can't make that too small because otherwise you'll screw
Yeah.
up the relic abundance. And now you
Yeah.
can just add a jet. So it seems like it's pretty constrained. It seems like there's not a lot of wiggle room there. I mean, of course, you can reduce the standard model coupling, right?
Yes,
But that's,
Yeah.
but I'm
And
saying that's what you're bounding, basically. You're basically would be bounding.
Yeah, so I want something where it's just a standard model coupling I'm studying. But yeah, you're
But
absolutely
I'm
right.
saying but if you think you know the relic abundance, then.
Which is,
still-
yeah, which is fair. And part of this is that there's also this whole story of asymmetric dark matter that we want to patch onto. But you're
So you don't know if how the monitor.
I'm not sure. Good. Okay. You can also ask about antiprotons. But what you ought to ask about, so these are not yet constraining, what you ought to ask about are the dwarf bounds. And this is actually now an old slide as of a couple of weeks ago. If you're looking for dark matter annihilation, you want to constrain dark matter annihilation, you should look for dark matter annihilation elsewhere. And these dwarf galaxies are these small satellite galaxies around the Milky Way, where you have relatively a lot of dark matter and not very much stellar matter. So they're really ideal. I mean, there's much less dark matter density, but if you sit and look at them for a long time, you can stack them and get a lot of information about whether or not there's actually dark matter annihilation. And this is really starting to look like it's poking into the regions that are favored by the Galactic Center. This smeared out blob is kind of taking into account the systematic errors. This is drawn artistically, not technically. So when people talk about this Galactic Center Excess, and they talk about dark matter interpretations, this is really the main thing to think about as a really big constraint.
I'm sorry, so what does this show me?
Yeah, so this is the annihilation cross. So this is looking at dwarf galaxies. So these guys have dark matter, not a lot of stellar matter. And so I can look at them and look for photons. And they don't see them in dwarf galaxies. And so this is a line which rules out annihilation cross-sections above this. So above these lines are ruled out. And these blobs here kind of represent the different models that populate the Hooperon, let's call it. And it looks like this line is really starting to eat into this model space that's preferred.
Now, there's a newly discovered dwarf galaxy where they saw a hint of a signal.
Good. So Reticulum 2 sees a hint of a signal.
Right.
But this is using past 7 data. So there were a bunch of papers a few weeks ago. One was from a subgroup of astrophysicists who published Reticulum 2. There is also a paper by the FERMI collaboration using past 8 data, so it's slightly more sophisticated. They include Reticulum 2 in their set of plots, and they didn't see anything statistically significant. So this, as I understand, is an open question. Okay, so as I wrap up, let me now go back to some cute ideas about model building. Okay, so this is almost textbook. If I want to have a spin 1 mediator, I expect universal couplings to quarks. So a good template for this, at least phenomenologically, is gauge baryon number, just to get the signals. For a spin 0 mediator, by standard model gauge couplings, you expect to have something where you interact with the Higgs. So this is like a Higgs portal. And this is why a lot of people like thinking about the NMSSM as a way to populate these models. Right? The NMSSM gives you these additional scalars which you can use as mediators. But one thing which we've been playing with, and this is really just a promotional cartoon, is to get the pseudoscalar mediator without the scalar in composite Higgs models. Right? So there have been a lot of papers about MSSM, NMSSM, XYZ MSSM, where you find ways to get the additional scalar because you put in an extra complex Higgs. And that's fine, and you can play with tan beta and do all of these things. But there's also a way to connect the mediator to electroweak symmetry breaking that does not require an additional scalar. And that's through the composite Higgs mechanism. Where now, instead of having composite Higgs with a particular coset, this is one of John's favorite games, you can enlarge the coset and have additional pseudoscalar mediators.
Why is not the 2 Higgs doublet model a perfectly good way of doing this?
Good. It is.
Oh,
It is.
okay.
Yeah. So, yeah. No, I think we're both perfectly happy at this stage. I'm just pointing out that there's additional UV space.
Sorry, in this case, does dark matter needs to carry electrical charge?
No. So the mediator is a standard model singlet coming from a larger coset space. So the template is SO6 to SO5. Okay, and let me finish by talking about these dwarf bounds, which I really think are the most serious bounds for a dark matter interpretation for this excess. Here's the formula, right? Dark matter annihilation gives us gamma ray photons. Cool. And this formula gives us tension with the dwarfs. Maybe it's real, maybe it's maybe we're still okay, but it looks like there's tension. A recent way to get around this is to change the formula. It's not just a dark matter annihilation giving you the photons, but dark matter, so remember the story, dark matter annihilates into electrons, and the electrons upscatter ambient starlight. And this is really cute because we have lots of ambient starlight in the galactic center, but the dwarfs, by definition, do not have a lot of starlight. So with this kind of diagram, you actually get a reasonable fit to the galactic center, and you can avoid the dwarf bounds. Now, you're out of the what does it say? Out of the pot into the frying pan. Because now if you go into electrons, you're injecting positrons, and positrons, this gives you a positron bump, which is constrained by Pamela, and soon also AMS. And let me skip the self-interacting dark matter additional thing. The current thing that we're doing to avoid this is instead of having a mediator go into 2 electrons, go into an electron and a muon. Go into 2 muons, but the muons being off shell. And this smears out your electron spectrum, while hopefully still giving you the galactic center spectrum. And this whole thing, it actually works out very nicely in a Fermi-Nielsen mechanism. I guess Fermi-Nielsen, you can get whatever you want, but this also suppresses your mixing with the Higgs, which means you can get this mu-E coupling, for example, without really picking up too many Higgs couplings. And just as a side punchline for this thing, if you think about flavor violating interactions in the quark sector, you can even have top charm. So typically people say dark matter going into tops doesn't work for the galactic center because tops are so heavy, but a top charm pair is not so heavy. And what you can see here, the red is the spectrum from top charm with dark matter is 120 GeV. This actually looks very similar to dark matter going into BB bar, where dark matter is 100 GeV, and they both seem to fit the envelope very naively. So this is another direction, kind of playing with flavor bounds for this excess. All right, so here's my...
But the top will also give you some lepton, not necessarily.
Yeah.
With the top decay also give you power leptons.
Well, most of this is because top gives you lots of bottoms. Yeah. And the leptons are softer, but yeah. Okay, so here's the pictorial summary. So we started by talking about the importance of simplified models and the physics of the mediator for dark matter searches. We talked about this scenario where this limit of this corner of theory space where you go into on-shell mediators. And then we said, okay, this thing can give us the Galactic Center Excess in an interesting way, a way that naively avoids a lot of the typical bounds for dark matter. And then we talked about, well, there are other ways to probe this scenario, and these scenarios, which are kind of interesting, independent of the Fermi excess altogether, right? The idea of using composite Higgs to give you mediators rather than dark matter, or looking for low mass diphoton resonances, are things which are kind of cute on their own right. So I think with that, I'm out of time. So thank you very much for having me.
Questions that were not asked during the talk?
Just one question. So what's that time scale of 1 million years for an electron event? Is that just diffusion?
Yeah, that I think so. I'm not sure.
Footprints of such an event, what's the...
Yeah, that I'm not sure. So yeah, the
Extinction of the dinosaurs.
yeah.
Or people.
Yeah, that I'm not sure.
So when you said that mediator propagates, how long do you think?
Good. Yeah. So let's see. The bound, yeah, good. So this is another way of asking, what is the bound on the couplings in standard model just from the morphology? So you can imagine that maybe this propagates so far, how long does it take before you really see a difference in the morphology of the excess? I think the thing which happens first is that the coupling of the mediator to the standard model, this thing plays an important role in the thermal relic story. So when I go through the Boltzmann equation to find whether or not this dark matter is a good thermal relic, everything is fine as long as the thing I'm annihilating into is in thermal equilibrium. So in fact, the upper limit on this thing, the lower limit on this thing, comes from ensuring that when the dark matter freezes out, the mediators are in thermal equilibrium in the standard model. And that's why, yeah, so at some, but this question of the morphology is actually a good question for like an undergraduate E&M course, just solving using Green's functions.
Last question. Ryan, which one is God and which one is Adam?
It's the one that looks like Susskind is God.
It's like it's symmetric.
That's true. Yeah, well,
Maybe a last question.
yes.
In the compositics idea where the mediator is pseudo-Goldstone, what is the dark matter then? It's
An additional state which adds to the breaking of the symmetry.
can be a baryon or
Could be, but we're not even that sophisticated. We're just doing the dumbest thing and saying, okay, you have a bigger coset space. I stick on an additional source of breaking, but just from the matter fields.
And then the other thing is there, you said this SO6 to SO5 model, right? You get just one extra Goldstone. But then I thought that, this Goldstone will decay mostly in Z gamma, basically, instead of gamma gamma, because of the symmetry. We can talk about that.
Yeah.
I think it's most helpful.
Yeah, let's talk. I have some notes on this. We can talk about it. So. Yeah. Good.
Any other questions? Let's thank Flip again.
So this one is yours, right?
Oh, yes.